paramagnetic susceptibility out of the numerically obtained curves. And it goes like 1 over T minus Tc. So if you plot the paramagnetic susceptibility in the paramagnetic phase, it goes like 1 over T minus Tc, which diverges from the positive side at Tc. While if you completely ignore the Heisenberg interaction or mean field, then the curve, according to Curie's law, should diverge only at 0. So here, the curve turns from 1 over T to 1 over T minus Tc, giving you a finite value of Tc, and the Tc is attributed to the spin-spin interaction, which has the electrostatic origin. Okay. However, the mean field models, well, even we tolerate the discrepancies with the experiment, still suffers a serious problem. So the mean field model works fairly well in 3 dimensions. It becomes increasingly inaccurate in reduced dimensions. For example, if you study 2D or 1D materials, the mean field model will typically give you a wrong answer. And that is because the spin fluctuations are enhanced effectively by the reduced dimensionality. So the ignorance of the spin fluctuations in the reduced dimensions in 1D or 2D becomes, unacceptable. And the spin fluctuations are so critical in reduced dimensions such that even the entire magnetization, the entire spontaneous ordering will be removed in reduced dimensions. And this is known as Merman-Wegener theorem, saying that if the microscopic spin-spin interactions is fully isotopic in space, then strictly there will be no spontaneous ordering at any finite temperature in 1D or 2D, unless you have a magnetic anisotropy. So nowadays we know that there's abundant 2-dimensional magnetic materials which does order at finite temperature. But that is where the Merman-Wegener theorem does not apply because of the magnetic anisotropy. The theorem applies to the isotopic spin-spin interaction. In the presence of a magnetic anisotropy, the spin interaction is no longer isotopic. That brings us to the next topic, the magnetic anisotropy. I will try to finish within 10 minutes. The magnetic anisotropy. So, like I said, we could always classify magnetic interactions in terms of the physical origin or in terms of geometry. Let us go with the physical origin classifications in the magnetic anisotropy. The first type is called magnetocrystalline anisotropy, which is attributed to the spin-orbit coupling. The spin-orbit coupling again, that entangles the spin orientation with the local crystal environment. So in terms of the spin, well, by virtue of the spin-orbit coupling, a spin orientation is no longer isotopic in space because now it effectively sees the crystal orientation. For example, this direction gives me a lower energy than this one, okay? But if you turn off the spin-orbit coupling, the spin de Graaff will become decoupled from the crystal environment. So it will simply disregard this crystal environment. That's why the anisotropy has to do with the spin-orbit coupling. Okay, so this is from the physical origin. Now, for the magnetic anisotropy, we could also classify it from a geometrical perspective. And the simplest magnetic anisotropy is the uniaxial anisotropy, naming that throughout this 3-dimensional space, there is one direction that is special. Okay, one direction that is special. So this direction could either define an easy direction or a hard direction. For the easy direction, all spins want to align in that direction. For hard axis, all spins want to be perpendicular to this direction. So the hard axis also defines an easy plane. That's why the hard axis anisotropy is equivalent to an easy plane anisotropy. But hard axis or easy axis, they are both uniaxial. You know, what is being called uniaxial? Uniaxial, contrary to the unidirectional interaction, that defines a mutually equivalent positive and negative interaction, meaning that the spins could either be pointing this way or this way, equally heavy. So this is called the uniaxial. What is the unidirectional? Unidirectional means positive and negative are opposite. So for example, the Z-man interaction is unidirectional. If you apply a magnetic field, you select out either up or down, but not both. For the magnetic anisotropy, it's uniaxial. Okay? So what if the uniaxial anisotropy is in the hard direction, defining the easy plane? So for easy plane materials, typically there will be a secondary anisotropy axis within the easy plane. And for example, this is the nickel oxide, where the 111 plane is the easy plane. So all the spins are lies in the 111 plane. But within the 111 plane, there is a special direction 112 bar that is the secondary easy axis with a much weaker strength, but it exists. So the nickel oxide exemplifies the easy plane materials where there are two anisotropy axes. One hard axis, the primary axis, and a perpendicular easy axis, or the weaker or secondary axis. Okay. So this is the easy plane. And yet there's a complicated case called a cubic anisotropy. For example, the nickel and other transition metals, I believe. So here, the alpha, beta, and the gamma are the directional cosines with respect to the XYZ axis in a simple picture. So if you have a cubic anisotropy, for example, the 111 direction marks the easy direction. So the material could be easily polarized if you apply the B field along the easy direction, the 111. But relatively speaking, the 100 direction defines the hard axis. So if you turn your magnetic field in the 100 direction, the material becomes, substantially harder to polarize. So this is the cubic anisotropy, which is more complicated. And experimentally, it is very important. I mean, the magnetic anisotropy is one of the most critical information about a magnetic material. So typically, experimentalists want to quantify the magnetic anisotropy, determine which type it has, by applying a magnetic field in multiple different interactions, and then analyze the data. Okay. So another physical origin that gives rise to the magnetic anisotropy or anisotropic behavior is called the shape anisotropy. Well, the magnetocrystalline anisotropy is intrinsic, this is extrinsic, or external magnetism. And the shape anisotropy, as the name indicates, depends on the geometrical shape of the material. The same material for bulk and the thin film, they could be very different. It's that simple. Okay? So the shape anisotropy primarily originates from the dipolar interaction. We know the dipolar interaction is much weaker than the exchange. However, at long distances, the dipolar interaction could be very critical. So we know that the magnetic field B must have a closed line, so it's a divergenceless. But the magnetic field H, it could, have a terminals, especially when the magnetization becomes discontinuous. For example, on the interface of a magnetic thin film. On the interface of a magnetic thin film, the magnetization vector jumps to 0. So the interface marks where the magnetization becomes discontinuous. And that effectively gives you artificial magnetic charges, similar to a capacitor. So the accumulation of the artificial magnetic charges on the interface of a thin film gives you a what is known as a demagnetization field that tries to push the magnetization vector back to the in-plane direction. So the dipolar interaction in the form of a demagnetization field defines an effective hard axis anisotropy. So basically, if the magnetic moment is perpendicular to plane, then you are going to pay a high energy penalty because of the dipolar interaction. So the dipolar interaction want the magnetization to be lies in plane in order to minimize the artificial magnetic charge. But microscopically speaking, this is extrinsic mechanism. Okay. Well, this is just the simplest demonstration of the shape anisotropy. What if I do not have a simple magnetic thin film? I have, an arbitrarily shaped magnetic material. Then the calculation of the shape anisotropy is very computationally costly. It could even blow up your computer. Okay. All right, so, I'm running out of time, so let me skip this, but this is a revisit of the magnetic hysteresis loop. So, magnetic hysteresis loop is a fingerprint of ferromagnetism, and microscopically it is attributed to the existence of magnetic anisotropy. So, because of the magnetic anisotropy, then if you already saturate the magnetization and then turn off the field, the material does not go back to randomization. It has a remaining finite value of magnetization called remanent magnetization. And the stability of the remanent magnetization is directly related to magnetic anisotropy. So, qualitatively speaking, the larger the magnetic anisotropy, the wider the magnetic hysteresis loop. So on the loop, the negative field to completely undo the magnetization is called coercive field, or simply coercivity. And it is the coercivity or coercive field that is directly determined by the magnetic anisotropy. So in real materials, the value of magnetic anisotropy spans about, several orders of magnitude. For the small loop or narrow loop or small coercivity field, this is called a soft magnet, where for wider loop material, it's called a hard magnet. It's hard because it's hard to undo this remanent magnetization. So hysteresis loop as a direct consequence of magnetic anisotropy that also defines, distinguishes hard from soft magnet. Well, soft and hard magnets have a wide range of applications. For example, in like in transformers, you do want a hard magnet. But in spintronic materials, to easily toggle the logic, to easily toggle the logic, you want the magnet to be fairly soft. So soft and hard magnets have different applications. Okay. So let me just quickly jump into our last topic because we are actually behind the schedule. So the hysteresis loop only tells us the overall behavior of the magnetization process. But if we zoom into the microscopic details, then you will realize that the magnetization process is actually achieved by very complicated motion of magnetic domains. So for a large material, like I said, the long-range, weaker dipolar interaction breaks the materials into multiple domains. Some domains are more aligned with the magnetic field, some are opposite. But by increasing the magnetic field, you are energetically enlarging the heavy domains while shrinking the unheavy domains until eventually the heavy domains has eaten all the unheavy domains, completing the magnetization process. So the magnetization process actually involves a very complicated domain wall motion. And that brings me to the last topic, which I only have 1 minute to comment. So for a domain wall, I mean, separating two domains, if we zoom in the domain walls, then we will realize that the spins does not simply, goes here and suddenly flip. That's not what is happening, because that pays too much energy penalty. To study the domain walls, we actually have to look into the dedicated energy competitions between 3 parties: the exchange, the magnetic anisotropy, and the long-range dipole-dipole interaction. Okay. So for today, we do not have time to go into the details, but the amazing thing here is that even with the complicated interactions, we are still able to obtain an analytical expression for the spin profiles across a magnetic domain wall. And that profile is widely known as the soliton profile. It's a soliton. So this is a standard soliton profile. Once again, the math, we do not have enough time to appreciate the math, but you should be, bear in mind that the magnetic domain walls, or generally the magnetic spin textures, is a compromise of different competing magnetic interactions. And for 1D domain walls, there are 3 competing parties: dipole interaction controlling the long-range behavior, the exchange interaction dominating the short-range behavior, and the magnetic anisotropy is fully local. Okay, this is the magnetic domain walls. And for the domain walls, we also have the so-called Bloch walls and the Neal walls. Well, for the Neal walls, if I go here to there, the spins are rotating in the plane encompassing the lines, the domain wall direction. Well, for the Bloch walls, it rotates this way. Okay, this is the Bloch wall. So, well, whether a material prefers Bloch wall or the Neal wall, that also depends on the size of the material. And once again, this is a complicated compromise among 3 interactions: exchange, anisotropy, and the long-range dipole interaction. The conclusion is very important. Okay. And so the one-dimensional domain wall solution can be, or soliton solution, can be directly generalized into higher dimensions. For example, in 2 dimensions, we have 2 different types of magnetic spin texture: the magnetic vortex and the magnetic skyrmions. So the skyrmions and the vortex, they are topologically very similar, but they are geometrically very different. A heuristic way to understand the difference between vortex and the skyrmion is to look at the spins surrounding the center. So while the center spin in the magnetic vortex could be pointing outward, while all other spins should be strictly confined in the magnetic film plane. So this is magnetic vortex. Well, in the magnetic skyrmions, there's no singularities in the center. So the spins in the radial direction smoothly vary as if this is a domain wall. So if you take a cross-section, you cut this through and look at the radial spin profile, it just looks like a domain wall. But this is not the case in magnetic vortex. And in 3 dimensions, we could have magnetic monopoles, and also recently there's, a new theoretical proposals of what is known as 3D Hopfions. Okay. But unfortunately, we do not have time to talk about these interesting stuff. And I'm already over the time. So I would like to thank you very much for attending my lecture. And feel free to take a break, but I will stay here for just in case we have more questions.
So if you have more questions, you can approach Professor Cheng later during the break or throughout the week. And just some public announcements. So we have cakes and sandwiches just outside, and